Hello and welcome to this topic, the application of differentials. Let's see some interesting examples. First, let's do one example of change of the geometric form. This example has to do with the Earth. Suppose you took the entire Earth and imagine the Earth a literally perfect sphere. Of course, it's not quite, but imagine it is a perfect round sphere. Now, suppose we take the entire equator of the Earth, which is about 25,000 miles around, and we put a belt around the Earth. And you see this very attractive belt in this graph, just snugly around the Earth. As we supposed, the Earth is perfectly round, so the belt just touches every point. It's just the length of the equator, about 25,000 miles. Now we say, I think that belt is a little tight, and the Earth needs a little breathing room, and so we decided to loosen the belt a little bit. The way we loosen the belt is that we just add a little more length to the belt. So we add another 7 feet to the belt. So the total length is about 25,000 miles plus 7 feet. So the belt is slightly off the equator of the Earth. Now I'm going to ask you a question to see how your intuition is. So the question is, how far from the Earth do you think that the belt would be? I'm going to give you a few seconds to think about this, to make a guess. So, do you think you could crawl under it? Kathy, what do you think about it?
I think the belt will be very close to the Earth. Maybe just a hair can go under it.
Yes, thank you, Kathy. My intuition told me the same thing as yours. Yes, most people with intuition that if you add 25,000 miles with 7 feet, they will be going to think this belt is just barely off the ground. So, is that the true answer? Actually, the belt is just about a little more than 1 foot off the ground, and you just could crawl under it everywhere around the equator. How could you see that? We can see it by thinking about what the increase of the radius is of the circle, which is adding 7 feet to the belt, and what is the relationship between the change of circumference and change in the radius? Because the change in the radius is corresponding to how far that belt would be off the Earth. Now, let's think of this formula. Make the relationship between the radius of the circle and its circumference. The formula is quite simple. So the circumference is 2 pi r. The derivative of the circumference is 2 pi. So by differential, we know that delta c is approximately equal to c prime r times delta r. So it's 2 pi times delta r. And delta c is equal to 7 feet. In the other hand, 2 pi is less than 7, so delta r is a little bit more than 1 foot. The derivative c prime r is 2 pi, means for every change in radius will approximately lead to 6.26 feet change in circumference. This is sort of something often challenges the intuition. That makes things funny, isn't it? Alright, now let's see one example from biology. Jack, would you like to read this problem for me?
Okay, in biology, Poiseuille's law for blood flow says that the volume flowing through an artery is proportional to the fourth power of the radius, that is, V equals K times R to the fourth. But how much must the radius be increased in order to increase the blood flow by 50%?
Fantastic. Thank you, Jack. Let's solve the problem together. First, let's find the differentials. So, the differential of V is equal to 4kr cubed dr. And the relative change in the volume is delta V over V, and it's approximately equal to dV over V. So we plug in dV, then we will find it's equal to 4 times dr over r. So for a 50% change in volume, we know 50% is approximately equal to dV over V, and is equal to 4 times dr over r. Then, the relative change in r must be delta r over r, approximately equal to dr over r, and is equal to 0.5 over 4. We find that it's 0.125. That's just a 12.5% increase in the radius of the artery will increase the blood flow by about 50%. Alright, let's see another example from special theory of relativity. Jordanson, would you like to read this problem for me?
Yes. Example 2. Einstein's special theory of relativity says that an object's mass, m, is related to its velocity, v, by the formula m equals m0 over square root of 1 minus v squared over c squared. Here m0 is the rest mass and c is the speed of light. Use differentials to determine the percent increase in the mass of an object when its velocity increases from 0.9 c to 0.92 c.
Thank you so much, Jordanson. Let's solve the problem together. The percent increase in mass of an object is delta m over m. First, we find the differential dm by chain rule and simplify it as following. So we solve it by chain rule and find dm. Then we use dm over m to approximate delta m over m. So delta m over m is approximately equal to dm over m. Then we plug in dm and m. We will find that delta m over m is approximately equal to v over c squared minus v squared times dv. Now we plug in v and dv. Then we will find the answer. So v is 0.9c, dv is 0.92c minus 0.9c, and it's equal to 0.02c. So dm over m is approximately equal to 0.095. Then we find that the percent increase in mass is about 9.5. Maybe this problem is very hard, but it's very interesting. Alright, we discussed some examples this class, such as the belt of the earth, the flow of the blood, the special theory of relativity, and so on. Hope you enjoy them. I'm looking forward to seeing you in next class. Thank you.